So that should be enough of our housekeeping. I'll get on to the introduction. So today I will just give a brief introduction as per the usual format, starting with a safety minute, an introduction to Geosyntec Consultants, and to our speaker today, and then I'll hand over to Sandra for our presentation topic. So for the safety minute topic today, I've selected sample packing and shipping, and this is probably the aspect of treatability studies that our clients are coming most in direct contact with. That is actually getting us the sample material in order to conduct these studies. So from a safety perspective, one of the key issues with sample handling is the manual handling of eskies filled with samples and ice or cooler blocks. As many of us know, these things get really heavy really fast. It doesn't take that many samples for your esky to become fairly yieldy. And this is not rocket science, but just fill your coolers to the weight that you are comfortable lifting. Maybe plan on having extra coolers on hand rather than try to shove everything into the smallest number of coolers. You'll save your back, and you'll avoid injury doing it this way. And of course, always use proper lifting technique when lifting heavy coolers. This is probably more of a quality issue than a safety issue, but we strongly recommend using blue ice blocks rather than wet ice for keeping samples cool. The main reason for this is that when ice melts, your samples are floating around in meltwater. The potential for cross-contamination is much greater. It can be a safety risk if there is transfer of contaminants into that meltwater and, for example, you get a leak from your cooler during transport. So I strongly recommend using blue ice blocks rather than wet ice. And this just takes a little bit of advanced preparation because you can't often go to your local market and buy frozen blue ice blocks. You just have to have them on hand the night before. If you're transporting your samples yourself, if you're not getting them picked up from site by a courier, just make sure that your coolers are well secured. Often coolers have a hard plastic shell that can slip and move around very easily if you have to slow down quickly, if you get rear-ended, if you're in an accident. And a heavy cooler moving at high speed in your vehicle is an extremely dangerous thing to happen. On the lighter side, you may break your sample containers. On the worst side, you can have devastating injury from this sort of thing. And finally, with shipping your samples, just ensure that on your shipping waybill, your sample shipment complies with any local or international regulations regarding dangerous goods. Now, as Sandra will touch on in this presentation, the shipping of environmental samples to Sirem Lab does not constitute shipment of dangerous goods. We do have detailed guidance in that regard that we provide to our clients when they're shipping samples. It is not a dangerous good shipping situation when you are shipping environmental samples to us, but as a general precaution, if you're ever shipping around samples locally or internationally, just check first that you're in compliance. So moving right along, Geosyntec Consultants, who are we? Well, we're an environmental consultancy that was founded in the States just over 30 years ago. We have a bit over 1,000 employees based in a bit over 60 offices. Our primary base is in the United States, but we have local presence in Australia, Canada, Malaysia, the United Kingdom, and we service a lot of markets beyond those from those hubs. As an overarching view of Geosyntec Consultants, we really focus on targeting the difficult work, the challenging work, the projects that others may not be equipped to deliver or provide advice on. And we do that by really targeting staff with excellent academic credentials, excellent industry experience, and facilitating that to provide advice that others others may not be able to provide in our field. Geosyntec Consultants is a family of companies. Some of those include Sirem. That will be the topic of today's discussion. Sandra will cover Sirem's capabilities in great detail, so I won't address those now. MMI Engineering, which is a safety and risk engineering consultancy, focuses on the quantification and management of risk posed by natural hazards and industrial process hazards. Savron, which is a company that licenses a remediation technology developed by Geosyntec, which is the STAR technology, which is based on smoldering combustion of dean apples. It's quite an interesting technology and will definitely be one of our upcoming topics. There is one I haven't listed here, which is our newest member, OptiRTC. I will hold on giving details on that one until I've actually got it up on the slide, but newest member of the Geosyntec family. On to our presenter today. Our presenter is Sandra Dworczyk, who is a senior manager with Sirem. And suffice it to say that Sandra has lots and lots of experience with the design and the implementation and the interpretation of laboratory studies to evaluate remediation techniques for soil, groundwater, sediment across a broad range of remediation types and techniques. I will let Sandra take it from there, as that is the topic of our discussion today. Sandra, thank you very much for your time and for, as always, accommodating our time zone differences. And without further ado, over to Sandra.
Thank you very much. Good evening, everyone. So I'd like to introduce you to Sirem. My name is Sandra Dworczyk, and I'm on the photograph on the slide here. I'm on the very left-hand side here, and I am one of 3 senior managers at Sirem. I work with Phil Dennis, who's right next to me in the picture, and Jeff Roberts here over in the middle of the picture, and we all report to our director, Peter Dollar, who is a hydrogeologist. And so Jeff, Phil, and I are all environmental scientists, microbiologists, and molecular biologists, and we manage this group of laboratory technicians who are chemists, microbiologists, molecular biologists, biotechnology technicians, that sort of people, and in the laboratory at Sirem. Sirem has been around since 2002, and we provide laboratory testing services and products for remediation, not only of groundwater, but of sediment and of soil. We are located in Canada. We are west of Toronto, Canada, if you know where that is, a little bit, I guess, north of Niagara Falls, if you know that as a landmark in North America. And so I'm very pleased to be speaking to you today about Sirem. I've been doing treatability studies for Australian sites, actually, almost from the very time I started doing studies about 15 years ago. So it's dear to my heart, and I've had the fortune of coming over a couple of years ago for the Clean Up Australia conference. So I hope to get back as soon as possible, actually. Before our winter's over would be nice, but I'll see when that happens. Okay, use these controls. So here's the map where we are. So you can see in southern Ontario is where we're located, near Lake Ontario, and Toronto is just to the northeast of us. So today I'm going to be talking about our treatability testing services in general, but I wanted to start off first with the products and services that Sirem offers. We offer 4 main service areas: molecular genetic testing for microorganisms under the trade name of GeneTrack. So we use DNA-based technologies to identify microorganisms that are known to have specific capabilities related to bioremediation generally. And so we offer services that way, and we can provide sample filters for DNA extraction and offer all those services. We have bioaugmentation cultures, which have developed from our treatability studies originally and under the name of KB1 and KB1+. These cultures have been widely used worldwide and, in fact, have been applied in Australia. We have had import permits into Australia, and we anticipate actually shipping to another site in Melbourne, I believe, in March of this coming year. So It's a bioaugmentation culture for degradation of mostly chlorinated solvents in groundwater. I'm not going to touch on it too much, although it will come up in a couple of our treatability study case studies that are being presented. And finally, another product that we sell is the Waterloo membrane sampler. This is a passive diffusive sampler used for vapor intrusion applications. And if you have interest in that, you can go to the Sirem website and click on the link to the WMS sampler and get more information on that, or send me an email and I'd be happy to direct you to the technical lead for that as well. So I'll just jump in here and talk to you what is a treatability test. Obviously, it's bench scale testing in the laboratory, but we use actual site materials, and that's critical that we get site materials, whether it's soil or geological materials, probably a better description, sediment, rock, and site groundwater, and that it comes from the zone of contamination that you're looking at remediating. And that's very important that we want to get impacted material, because that's going to be most relevant to testing any technology, is we need to have the right matrix to make sure that the technology is going to be compatible with that. Can be done both in batch reactors or in columns that we construct in the laboratory. And they're very customized studies. Although we have standardized formats for a number of our different studies, we customize every treatability study to site-specific needs, and so we can address the specific objectives of remedial technology evaluations at sites. A lot of people question clients that don't want to necessarily spend a lot of money. They want to ask, why would you even bother with treatability test? Let's just go right to the field. And one of the main reasons is that you can evaluate a number of remedial options before you get to the field, and you can do it on a cost-effective basis, in that you can compare ISCO, chemical oxidation, versus bioremediation versus abiotic techniques. You can look at different zones of the site, and it allows you to optimize the testing for a specific remedy. So you might do a broad study where you're evaluating general broad areas, maybe 3 or 4 different oxidants perhaps, but then you can then also do a more specialized study that hones in more specifically on, what type of electron donor might you want to apply or work best to the site, what oxidant activation chemistry might work. And our studies are very flexible in that we can get relatively fast turnaround time on analytical data that allows us to make changes to the scope of the study without making huge changes in the cost of the study, because if a study is designed with a certain number of sampling events, that cost doesn't change. If we make one small change to a treatment, or what we call a change on the fly, it doesn't impact the cost at all. And so we can be very flexible and change direction. If something isn't working or something's working faster or slower than anticipated, we can address that immediately so that we can get the best output of results in time for deliverables for reporting to clients. And often treatability tests are used to reassure the stakeholders that remediation approaches are feasible before you go and spend a lot of money on a field implementation, either a pilot test or a full-scale application. And again, the performance of a treatability study will reduce the time and the cost of an application in the field. What types of information will you gain from a treatability study? Very obviously, you're going to get contaminant degradation rates. Is benzene going to be degraded? Is trichloroethene going to be degraded? Is what intermediate products are going to be produced? You can get information on amendments that you might add, whether it's an electron donor or an electron acceptor or a co-metabolite that you're adding. You can get some idea of how fast they're being consumed. In some cases, you can get elucidation of specific degradation pathways if they're not already well known. And very importantly, you can look at the effect of controlling variables, which can be very significant at some sites where you don't realize something has a stronger effect than you anticipated. pH and redox are very, very important, as well as contaminant mixtures. Individual contaminants may be able to be degraded in the laboratory, but the mixture testing in the laboratory is more important to understand as well. If you've got chloroform present with chlorinated ethynes, such as TCE and PCE, you need to understand what that means and what that might affect a bioremediation application. For using permeable reactive barriers, often with zero-valent iron or ZVI, you can get information that provides design information that allows you to design the residence time and longevity of a potential barrier application. So just a couple of visuals from pictures in lab. We put dirt in bottles. That's a lot of what we do. We use sacrificial or continuous batch testing, which we call microcosm studies. So there are some pictures with some very unusual looking site geological material in the picture here, sort of a side view along those bottles before they got put in an anaerobic incubator, as well as on the right-hand side here, a setup of all our column studies that we have in the laboratory. And so the two main areas are batch testing and column flow through testing. The types of treatability technologies that we can test in the laboratory are limitless. Generally, they fall under three main areas that we typically evaluate, but they can really be used to any sort of a technology that you do want to test. So for bioremediation applications, most often you're looking at either aerobic or anaerobic or co-metabolic applications. For chemical oxidation, we have extensive experience with persulfate permanganate and a little bit of experiments with peroxide and ozone. They're a little bit more volatile and challenging compounds to work with in the laboratory, but we have conducted them with some success. We can do oxidant demand, we can do treatability of actual compounds with the different oxidant chemistries that are available. And we often use reagents directly from vendors. So we want to use the reagent that's going to be applied in the field. So we'll try and obtain reagents right directly from a vendor that you might be using at a site so that we're testing the right material. Chemical reduction studies typically involve evaluation of zero-valent iron or ZVI in various different scales and other bimetallic metals that also can be tested. And other things such as reduced iron minerals, such as siderite, or other substrates such as mulch, which is often used in biobarriers. And this testing can be done in the different media that you have available to us, whether it's the site soil and geological material, groundwater, wastewater, surface water, sediments, pore water. All of those things can be tested in the laboratory. Some of them are a little bit more challenging to get samples of, pore water in particular, but most everything else it's easy to get the samples to be tested in the laboratory. The compound classes that can be tested in the laboratory also are limitless as well. We started off really getting our experience with chlorinated solvents about 10 to 15 years ago. We did a lot of treatability studies with trichloroethene and looking at biodegradation with the helicocoides organisms, but that's since been expanded to a wide variety of different chlorinated solvents, chlorinated ethenes, chlorinated ethanes, chlorinated methanes, chlorinated propanes, various petroleum hydrocarbons, pesticides, whether they're chlorinated or not, inorganic metals, and the list goes on. So, and much of that can be analyzed in-house in our laboratory, which is also what helps us control our costs of our studies, as well as we use local and regulatory approved analytical laboratories for some of the compounds that we don't analyze in-house ourselves. So now I'm just going to focus on how we conduct our batch treatability studies and give you a little bit more further information on those. So again, as I said, we construct them using site materials that you get from the zone of contamination. And what we typically do is we monitor contaminant reduction over time. And again, we customize the treatment variables to meet your site-specific needs. And in the photographs here, again, the bottom here, we have some petroleum hydrocarbons where we just have equivalent of vadostone soil with aerobic treatment. So you have these foam stoppers that are placed in these wide mouth bottles with a lot of air exchange that can be allowed through there, and looking at seeing what degradation you get in the soil phase. On the right-hand side of the picture is one of our anaerobic chambers where we incubate anything that needs to be kept under anaerobic or reducing conditions. When we get the materials from the site, we actually set up all our microcosms in chemical fume hoods. We've got the sash all the way up in our fume hood just so we could take a picture here. But we put all the materials into a temporary anaerobic glove bag. These have armholes in them here so that you can put your arms in. We remove the soil or the geological material from the cores and homogenize it. We have the groundwater in these carboys here that are typically 4-liter size. We measure out the soil either volumetrically or gravimetrically into sterile batch bottles, add the groundwater to them, all done for anaerobic studies under a gas mixture that keeps it anaerobic, or if it's aerobic, we'll just do it in the ambient air. And again, it allows us to set up these studies with no cross-contamination. So one study per disposable bag, the bottles are all set up and they're capped, and then they're transferred to the appropriate incubator, which is for anaerobic studies, an anaerobic incubator. For aerobic studies, it's just room temperature out in the laboratory. So this cartoon here just is a really good demonstration of how we design our studies. And one thing that we stress is replication. So most of the time, with some exceptions, we run everything in triplicate, and we find that triplicate reactors just allow us enough information about the variability of the data that you can trust things, and that duplicates, if you have one go one way and one go the other way in terms of results, you don't know which one's the right. Whereas with triplicates, you get a measure of the average and a standard deviation, and over time you get a really good understanding of the trends. We typically have controls for batch studies. For a biological treatability study, we'll have what's called a sterile control, where the site soils are autoclaved and poisoned, and the groundwater is poisoned to inhibit microbial activity, and also so that we can measure any abiotic and experimental losses. So any losses that might occur due to sorption or due to sampling variability can be measured in a sterile control. What we call an active control or an intrinsic control is simply just natural attenuation. We're not doing anything to those. We're not adding any amendments. We're just sampling it over time and seeing what happens, whether abiotic or biotic. And then we can look at, especially for treatability studies where you're looking at bioremediation, you're looking at biostimulation where you're adding either electron donors or electron acceptors, and looking at biostimulating. So basically you want to see if the indigenous microorganisms can be stimulated in their activity just by the provision of food. And you can also try other nutrients that might be added as well. Supplementally, we know that some sites don't have the right microbial populations for degradation, and so bioaugmentation cultures can be added to the microcosms and tested as well. And typically for anaerobic studies, you don't add bioaugmentation cultures until reducing conditions are achieved. And for aerobic and co-metabolic studies, we can add various gases to measure the impact of gas infusion, as well as the impact of co-metabolism. So for aerobic 1,4-dioxane co-metabolic degradation, you can look at using various alkane gases to promote co-metabolic degradation of 1,4-dioxane. And often for petroleum hydrocarbons, aerobic studies are quite often used to look at aerobic degradation of benzene BTEX compounds. Again, we must stress that our studies are custom designed for each site. So some sites might not want to look at bioaugmentation, and we take that one out. We may want to have additional controls. Perhaps we're going to adjust the pH. There's a variety of different things that can be adjusted, and that is usually at the proposal stage. We go through the site data with you when you're looking at trying to understand what you want to do for a treatability study and work that out right at the proposal stage. I'm going to jump right now into a case study. This site's in Denmark, and the contaminants of concern are 1,1,1-trichloroethane, or 1,1,1-TCA, and trichloroethene, or TCE. And the client objective of this study was to compare both bioremediation and in situ chemical oxidation. And so the first part that I'm going to present is some of the bioremediation results, and then I'm going to show you the base activated persulfate. I'm not going to show the results of the sterile control and the active control in interest of time. I will have another case study that does show some control data so you can see what you get in those types of results. So the first treatment that we looked at was emulsified vegetable oil amended and a bioaugmented treatment, and that's EVO is for emulsified vegetable oil. And both contaminants were at about approximately 5 milligrams per liter in the aqueous phase. So here you see the results presented in millimoles. So we've taken the concentration data and looked at the total mass of the contaminant in moles per bottle. It allows us to look at mass conversion. In bioremediation applications, you can actually see really good mass conversion, so it's a nice way to visualize the data. TCE is in the bright pink color. 111 TCA is in sort of the reddish-brown color. And you can see for the first 40 days of incubation, where it was incubated with an emulsified vegetable oil under anaerobic conditions, not much happened. We didn't really see anything move at all. So at day 41, we bioaugmented, and what we saw was rapid and complete dechlorination of the 111 TCA to chloroethane and the TCE to ethene, which is very typical for the bioaugmentation cultures that we have available. And it also shows really nicely the dechlorination sequence. So you see TCE in pink going to cis-DCE in the dark blue, going to vinyl chloride in the orange, and then ultimately to ethene. And you can see fairly nice mass balance with the amount of TCE that we started off with. And then the TCA degrading from the red into 1,1-DCA, which is the turquoise underneath here, and then going to chloroethane. Chloroethane is not further degraded under anaerobic conditions, but then can be degraded under aerobic conditions. And here are the results from an activated persulfate treatment. And what we saw, this was a much less intense study. We just did a quick snapshot after 14 days, and oxidant studies are typically very fast-moving and very quick. And what we saw was that all the chlorinated ethenes were degraded by 7 days very rapidly and as expected, and that 1,1 TCA wasn't as rapidly degraded, nor did we see complete degradation with the consumption of the persulfate. Ultimately, the client went to the field with the bio because it was the best option to treat all the contaminant classes. The next case study is a site in California where we are evaluating a bioremediation approach versus an abiotic degradation with zero-valent iron. And what we looked here was with trichloroethene at 25 milligrams per liter, which is pretty high for some sites, and hexavalent chromium at 70 milligrams per liter. And the treatments that we assessed here were intrinsic degradation with an anaerobic active control, microscale iron looking at the ZVI application, and an electron donor with and without bioaugmentation. So here's a really nice control. The study ran out a pretty long time. You can see it ran out over 200 days. And you see the main contaminants. We have hexavalent chromium, and that's in concentration in milligrams per liter on the right-hand axis here. And we have the chlorinated ethenes in total millimoles on the left-hand axis, and you see that the TCE showed a very small decline over the incubation period that's within the normal experimental variability of 10 to 20% is pretty standard for analytical and experimental variability. And we don't see any significant changes, in those over time. And you see that the total mass of chlorinated ethenes is pretty consistent as well. So in the treatment amended with microscale iron, you see very rapid degradation. One thing to point out was that the hexavalent chromium was so high that the water was yellow. So it was pretty toxic water. And what we saw amended with iron is we saw the hexavalent chromium drop out very quickly and down to non-detect concentrations within 40 days. We saw the chlorinated ethenes, the TCE drop out, and the cis-DCE drop out by about, between day 25 and day 30. We saw very little production of ethene, which is a typical result with ZVI. You often get acetylene being produced, so you're getting contaminant destruction all the way to acetylene, ultimately CO2, and so you lose all your mass, and that's a great result there. The electron donor treatment shows very clearly we get some degradation with the amendment of electron donor. What we see is hexavalent chromium dropping out pretty rapidly by day 100, and that we see TCE, once the hexavalent chromium was significantly reduced, we saw TCE being degraded to cis-DCE. But then after day 100, for the next 100 plus days, we didn't see anything happen. And so when we now look at our bioaugmented treatments, it's exactly the same as the previous treatment with the exception that it was bioaugmented just before day 150. And you can see the same results as before. Initially, hexavalent chromium dropped out. We didn't actually see the TCE go away at all in this treatment. Once we bio-augmented, then we saw cis-DCE and vinyl chloride being produced, with the production ultimately of ethene being produced, and a good mass conversion of all the moles of TCE were converted to ethene, which is very typical for chlorinated ethene bioremediation sites. So in this site, sorry, I'll go back to that slide for one moment. Again, the client went to the field with the bioremediation approach, and they did observe very similar results to what they saw in the treatability study. Sediment treatability testing, this is just sort of a placeholder to say that we can do a lot of treatability testing very similarly for sediment applications. The terminology is often different than for bioremediation and in situ chemical oxidation, where for sediment sites they're looking at something called monitored natural recovery, which is natural attenuation. Enhanced monitored natural recovery is where you're adding or biostimulating process to get degradation. Sequestration processes are where you're adding things to perhaps cause uptake of contaminants into solid matrices where things are bound up and you don't get any further mobilization of contaminants. And again, these are often laboratory bench scale studies, and we can use site material. So the photograph here is buckets of site materials here being homogenized through a large sieve into a mixing tank before we made our microcosms. So now I'll touch on our column treatability studies. Our columns are upflow columns. We pack them either with site soil, sediment, reduced metal, whichever you want to evaluate. We do upflow pumping up through the columns, and we monitor contaminant reduction along the flow of the column. It's more realistic to in situ conditions, and you can simulate mass transfer conditions and perhaps even observe some of the geochemical gradients that you might observe in the aquifer. So for biotreatability studies, columns allow us to test for PRB, so permeable reactive barrier designs, where you're looking at solid or slow-release electron donors. And you can see the gradient of conditions where you might, the front of your column study, you might see reduction of any aerobic conditions or oxygen, then nitrate-reducing conditions, iron-reducing, sulfate, and methanogenic conditions ultimately. It allows you to evaluate biodegradation along the flow path, calculates the half-lives, look at residence time and design thickness. So it can be quite a valuable tool to providing design data. Here's some photographs of some actual columns set up in the laboratory. One thing I'd like to point out is the zero-valent iron is actually black, so we've got granular zero-valent iron packed into the column here. We have a control here where we're not adding any amendments at all. In the biological column here, we've been adding electron donor, and what we see here is we see once the reducing conditions were established, you can see the blackening of the column around this port right here I'm circling, and that shows where we had establishment of reducing conditions for anaerobic bioremediation. We typically run 40 pore volumes. ZVI columns run typically 6 to 8 weeks. Biological columns run 6 to 12 weeks. The processes are just different time frames, but they're very useful for doing evaluation in a flowing system. So I've got a little testing results here from a treatability study that column study that we did in the laboratory. The residence time, or the distance along the column, is shown here, and we only sampled at the influent, the middle port, and the effluent port, and we have concentration in micrograms per liter looking at chlorinated ethenes. And you can see at the influent we had cis-DCE and TCE in the influent groundwater. Midpoint of the column, we saw some partial degradation. TCE is all gone, but we have cis-DCE and vinyl chloride still present with only a little bit of ethene. And then we get at the end point, the only place where we only saw an end product being breaking through. And it's very useful because this data can be then used to determine the minimum wall thickness. Reduced metal testing is being very widely used in column testing, in that the ZVI PRBs are well used in North America for treatment of chlorinated solvents and some metal plumes. And the design parameter data that you get allows you to understand degradation half-lives, the residence time of your barrier, your design thickness, as well as looking at what might happen to your iron. Is there something about the geochemistry of the groundwater that will passivate or foul your ZVI? And also even product selection, so evaluating different types or grades of iron or different vendors of iron products. And so this is a snapshot at a discrete sampling event from a column study looking at zero-valent iron, where we see a residence time or distance along the column. So if we have 7 sample events over 6 to 8 weeks, at each sampling event we'd get a snapshot just like this, and we'd see different results. In this particular case, we see the PCE and the TCE at the influent, which by about 6 hours of residence time is completely degraded in this particular case. So I wanted to just do a case study for a site, materials that we got from a site in Australia. This is an industrial site that had elevated arsenic conditions, and they were looking at understanding ZVI PRB design. And so they were very concerned about arsenic mobilization, and so they had a variety of different test objectives. So initially they said, are we going to get treatment of the arsenic in 2 different site groundwaters? So they provided 2 different groundwaters. They also wanted to evaluate 2 different iron sources to see if either one had a better removal capacity, as well as look at the stability of arsenic sequestered by zero-valent iron. So the arsenic was sequestered into zero-valent iron, and would it stably stay there, or would there be conditions under which it would be released? And also looking at because the receptor at the site was surface water, there was limitations as to where the barrier could be placed at the site. So they wanted to also look at the potential mobilization in the aquifer matrix down gradient of any barrier that they were going to put in. So my picture did not come up. Hang on a second. There we go. So in the photograph here, we have a picture of all the columns. Essentially, I'm just going to walk through a setup. And then there's 4 setups. In the little schematic here on the right, it shows we had 2 different groundwaters. We had 2 different irons. So there's groundwater 1 and groundwater 2. Then there's the con iron and the PL iron. So each setup here is identical, just one different variable. So in this case here, we're looking at the con iron with groundwater 2. This is the con iron with groundwater 1 and then groundwater 2. Column 1, which is this one here, was a ZVI to aquifer sequence, and this allowed us to get information about arsenic removal capacity and if the arsenic would be mobilized down gradient, because we took the effluent from the zero-valent iron column and put it through just an aquifer matrix column to see if the water coming off of the potential barrier would then strip any arsenic out of there. The column 2 was zero-valent iron run for a month with arsenic impacted water, and then flushed for an additional month with arsenic-free water to determine if the arsenic would be back leached from the zero-valent iron. And column 3 was essentially a replicate of column 2, but used as a sacrificial sampling device so that we could sacrifice that sample for spectroscopy and some of the leaching experiments that needed to be done. So the results are shown for one iron type but 2 different groundwaters. And this was the better performing iron. Just for the sake of time, I'm not going to show all the results. And what's shown is the C over C naught, so the concentration change over 10 profiles with increasing volume of water. And so these are essentially breakthrough curves. And as you see, the iron is getting used up or passivated, and so we see a progression of arsenic profiles. Arsenic 5 gets reduced to arsenic 3 and then complexes with iron and creates solid phases. So it creates passivation because it blocks the iron surfaces and doesn't allow it to be reactive any longer. And so you can see in groundwater 1, we did 60 pore volumes, and you can see that at this port here that I'm pointing to, at 60 pore volumes, we had breakthrough of the arsenic, whereas at 7 pore volumes, it was much less. And you can see in groundwater 2, we had much better treatment at this first port, and that, however, we did see breakthrough over time. Essentially, in groundwater 2, we had better removals, but no reactivity with time. and we had a lot less pore volumes in groundwater too. So we had some different results from each one of them, and they were very useful to the ultimate design of what they were going to use in the field. We also look at the cumulative mass of arsenic going through the column, and what this plot just shows that most of the arsenic was retained in the initial few centimeters of the column. And so you can see that the influent is the blue arsenic concentration, and port A, which is the first after 2.5 centimeters sampling port, the arsenic was there. And then what we did is we did leaching on the iron from that zone of the column, and we indicated that the iron was strongly sequestered. And then from the back leaching, we only just determined that there was 0.2% of the arsenic that was leached. So essentially the take-home message is that arsenic was strongly sequestered and not expected to be released from the spent iron. This is just I'm not going to go through all these results, but this technology was used scanning electron microscopy with an energy dispersive X-ray, and we used this to help understand where the arsenic went and how stable it was. Essentially, it shows that the arsenic absorbed onto iron oxide surfaces, and it was uniformly distributed. And so I'm not the expert in interpreting these ones. We use a local university at the University of Western Ontario to help us interpret these results. And this next slide here is the same technology, just a higher magnification, 2000x and then 1000x left and right. And it shows the actual crystals that developed on the iron grains. So all of this shows that the arsenic actually precipitated and created new secondary minerals with iron, which meant that it would be difficult for the arsenic to be removed with flushing. Again, just really good supportive information and data in understanding how the technology was going to work with the site groundwater. So again, we were able to successfully determine that ZVI removed dissolved arsenic in the 2 site groundwaters. We were able to determine specific removal capacities that were used for the design. We were able to demonstrate that there was limited mobilization in the sediment down gradient of that. And the scanning electron microscopy indicated where it was bound and that it was strongly bound. So I'm just going to start wrapping up now quickly so that we have some time for some questions. This table here is just a comparison of people wondering when would you do a batch versus column. And there's a lot of different factors. And so batch studies are significantly less expensive than column studies. We typically do treatments in triplicate, whereas column studies, because they're more time-consuming and more expensive, columns are typically done in single treatment. You can screen multiple options at the same time in a batch study, and often column studies are used more of an optimization step. Batch studies are 3 to 6 months typically, but they often can run anywhere from 4 to 12 months also. Column studies are flow rate dependent, so they can run anywhere from 3 to 12 months. Sampling events are multiple for both of them. Again, there's differences in the flexibility of the types of the studies, and the design information is significantly different as well. Batch studies are proof of concept. However, in column studies, you do get more hard design data that can be used for design of reactive barriers. I wanted to touch on shipping materials to our laboratory in Canada. I've been doing treatability studies with materials from Australia for a long time, and it's relatively easy to ship to Canada. We have done it with success with a number of different sites. And because environmental samples can be shipped as limited quantity exemptions or as samples for destructive analysis, there typically is no regulatory issues with shipping materials. We can't call it soil. Agricultural soil would require a soil import permit, but typically most of the work that we do is sediment and geological material that's from the deeper subsurface, so it's not going to fall under the rules of the regulatory agencies that are looking for soil pests and plant pathogens, which is typically why soil is regulated for its transport. But what we're going to transport is geological material that's, clay, silt, sands, gravels, and not things with plant roots and stuff like that in it. So We'll work with you to make sure you have the appropriate paperwork. We provide tracking of shipping and working out any holds that might occur. But with the right paperwork, shipments don't get held. I think that the point about packing your coolers so they're not too heavy is very important. Often it's the weight that determines the cost, not necessarily the dimensions of the esky or the cooler that you're shipping. And so we've got standardized protocols that we provide for both sample collection and for shipping, and we're always available electronically or on the phone to provide technical support and advice for shipping materials to us. So just wrapping up finally, we have the resources to perform studies that allow us to fully understand some of your most challenging problems at sites and help you deliver solutions to complex problems. These studies can be performed for a variety of contaminants in many different media under many different conditions. And so we really had a lot of success with treatability studies, and some of our best customers are repeat customers. Once you get a good treatability study done, they keep on coming back for more. We really enjoy good relationships with our customers and doing treatability studies. And with that, I will let Lang broker any questions that might pop up. Thank you for your time.
Okay, thank you, Sandra. Very, very interesting presentation. Just before we launch into questions, I'll just remind people that we will make available a copy of the webinar recording. It'll be a web and audio copy that will be available for download. I'll let you know when that's available. PDF copies of the slides will also be available if you want to be able to review those separately, but we would gladly take any questions from the group. If you want to ask them using audio, just click the arrow next to your name on the left of the screen and unmute yourself. Otherwise, give the Q&A button a go, and we'll answer any questions from the group. I might ask one in the interim. Sandra, how many Australian sites do you reckon we've performed treatability studies for?
That's a good question. At least a dozen or more. I actually haven't got a tally for all of Australia, but I know that one of the first ones I did back in, 2000 for before Sirem was actually officially Sirem was for one of the sites in Australia. So where we were looking at 1,2-DCA for EDC degradation.
Are there any questions from the rest of the group out there? Happy to take anything now. Happy to take anything via email afterwards as well. I'll follow up with an email to all the attendees that has our contact details, so we're more than happy to take questions afterwards if you prefer not to ask now. But please do feel free if you've got any burning questions right now. Hey, Prashant, I see there's a question coming through in a moment. Probably being formulated, so as soon as that comes through, we'll address that one. Okay, Sandra, can you see that question on your screen?
No, I can't.
Okay, let me read it out. It says, replicates are important in any treatability study, given the results are going to be used to conduct a pilot trial or even a full-scale trial. Also, soil is a heterogeneous matrix. Why is it that you recommend a single replicate for column study?
For column studies, it's cost typically what drives it. A triplicate column study is much more expensive, whereas triplicate batch studies it's not as expensive. And so it's for column studies, if someone wants to do it in triplicate, we'll certainly do it, but I think it's the cost that would drive the decision. You certainly can use a much larger sample size in a column study. You'll be using upwards of perhaps a couple of liters of soil in a column study, so you do have a larger sample of the soil, whereas in batch studies, the microcosms often only have 75 to 100 grams of soil in those ones.
Okay, there's another question that came through the Q&A. Looks like from Simon Mills. It says, hi Sandra, have you found persulfate with base activation is effective for petroleum hydrocarbon remediation in soils or sediments? We have done some trials in our lab over 2 to 7 days, and the process seems very slow compared to the expectations of some consultants. Do you have any thoughts on that one, Sandra?
Yeah, yes, we've found similar results that you don't get as necessarily, depending on the petroleum hydrocarbon mixture, base activation may not be strong enough. Often the trials, the challenges are the base activation itself. Often we'll do in our oxidant studies an evaluation of how much hydroxide is required to keep the pH above 10.5 or even above 11 to keep the persulfate activated. And we certainly see, depending on which petroleum hydrocarbon, different effectiveness. And sometimes it works and sometimes it doesn't. There's not always a consistency in some of those results. It often is contaminant driven, and people might want to try and have a more stronger activation chemistry, maybe perhaps looking at peroxide activation. One of the challenges with peroxide activation is a lot of gas generation.
Simon, it's worth noting as well, our next webinar topic is likely to be ISCO by one of our top practitioners. So that question can probably be reposed in that format as well, and sort of pick his brain as well when that one comes up. Any other questions from the group? Okay, we seem to probably be petering out on the questions unless there's any, what? Okay, sorry, jumped the gun. Another question for Prashant. In your chromium treatability study, hexavalent chromium was reduced to trivalent chromium. Did you look at removing total chromium too? If so, how?
Good question. I think I'll have to get back to you on that one. I don't have that result in front of me. I think we were looking at cumulative arsenic mass reduction, so I'll have to see if they summed that one into it. I'll have to get back to you.
Okay, any final questions out there? We're just on 1 o'clock now, so in lieu of any further questions, I'll thank everyone still on the line for your attendance today. We do appreciate you coming along to our webinars. Hope you find them useful. Hope you find them interesting. And a big thanks in particular to Sandra, who's 9 p.m. now in Guelph. So thanks very much for accommodating the Australian time frame. And like I said, I'll follow up with an email summarizing some details about access to the recording of the webinar, a copy of the slides, emails, and phone numbers in case you want to ask us questions separately. And as I alluded to, our next webinar is likely to come up late March or early April. The topic is going to be ISCO, and we will pass on more details at the time. Okay, thanks again, Sandra, and everyone else, we hope to see you in 2 months' time.